Imagine waking up tomorrow, and scientists tell you something has been discovered. An asteroid. Not a small one. A mountain-sized object, moving directly toward Earth. There is no bunker big enough. No city that can simply move. And if the asteroid is large enough, the entire planet becomes part of the problem. But here is the question that matters. Could we stop it? Not destroy it like Hollywood, but change its path just enough to make Earth and the asteroid miss each other? Can humans stop a planet-killing asteroid? Empty space. Our planet moves through a solar system filled with ancient debris left behind billions of years ago. Earth is not traveling through empty space. Our planet moves through a solar system filled with ancient debris left behind billions of years ago. The enemy we cannot see. Most of these rocks will never come close to us. But some follow orbits that cross Earth's path, turning ancient pieces of the solar system into potential threats. And the first rule of planetary defense is brutally simple: you cannot stop what you cannot find. Imagine scanning millions of stars when one tiny point moves differently from everything around it. That tiny movement could become the most important discovery of the night. Scientists don't simply find an asteroid. They track it repeatedly, measuring its position and calculating the orbit that carries it through the solar system. Because when it comes to an asteroid, time may be our greatest weapon. 20 years of warning can completely change the problem. If you change an asteroid's velocity by a tiny amount early enough, its position years later can shift by thousands of kilometers. Think of someone walking toward a doorway. Move them only a few centimeters sideways, and they still reach it. Move them early enough, and they reach somewhere completely different. Space works the same way. We don't need to overpower the asteroid. We need to give its future trajectory a small correction. And humanity has already tested one way of delivering that correction. In 2022, NASA sent a spacecraft toward an asteroid on purpose. The mission was called DART. The Double Asteroid Redirection Test. Its target was Dimorphos, a small asteroid moonlet orbiting a larger asteroid. DART approached at roughly 22,500 kilometers per hour. The spacecraft had one job: hit the asteroid. There was no second attempt. No pilot. No way to turn around. DART struck Dimorphos, and humanity watched. This was not an attempt to destroy the asteroid. It was an experiment. Could humanity deliberately change the motion of another world? The answer was yes. NASA found that DART changed Dimorphos' orbital period by roughly 32 minutes. A spacecraft had measurably changed an asteroid's motion, but the impact revealed something even more important. DART didn't simply push the asteroid with the spacecraft's momentum. The collision blasted material away from Dimorphos. And as that material escaped into space, it created additional recoil. Imagine standing on a skateboard and throwing something heavy backward. You move forward. The asteroid experienced a similar effect. The lesson was enormous. We don't necessarily need to overpower an asteroid. We need to change its trajectory. But then comes the uncomfortable question. What if the asteroid isn't 160 meters wide? What if it is a mountain? A larger asteroid contains vastly more mass. Changing its motion would require far more energy, more preparation, and probably more than one idea. And asteroids are not identical. Some may be solid rock. Others may be loose piles of rubble held together by weak gravity. Some rotate rapidly. Some have strange shapes. And until we study them closely, we may not know how they will react to an impact. Then there is the solution Hollywood has taught us to imagine: send a nuclear weapon into space and blow the asteroid apart. But blowing apart a dangerous asteroid could create another problem: multiple fragments, potentially still traveling toward Earth. A planetary defense is therefore about control. The goal is not necessarily to destroy the object, but but to make it miss. And perhaps the most important weapon against an asteroid isn't a weapon at all. It is a telescope. Some potentially dangerous objects are difficult to see because they are dark, distant, or approaching from parts of the sky that are difficult to observe from Earth. NASA's planned NEO Surveyor mission is designed specifically to help find and characterize potentially hazardous near-Earth objects. Its mission represents a simple idea: the more of the sky we can search, the less likely a dangerous asteroid is to surprise us. Imagine scientists discover a dangerous asteroid 20 years before impact. First, they observe it. They calculate its orbit. They determine its size, shape, rotation, and as much as possible about what lies beneath its surface. Then engineers design a spacecraft specifically for that asteroid. They choose the method based on the threat and the time available. A rocket launches from Earth. Months or years later, the spacecraft begins its journey toward the asteroid. The spacecraft arrives. It doesn't need to completely destroy the asteroid. It only needs to change its future by a small amount. Then humanity waits. The asteroid continues through space. The numbers are recalculated again and again. Now change the scenario. Instead of 20 years, imagine only one. There is less time to study it. Less time to build a spacecraft. Less time to launch. And fewer opportunities to correct a mistake. And even the asteroid's exact trajectory may still carry uncertainty. A tiny error in our measurements can matter enormously when billions of kilometers are involved. The nightmare isn't simply a big asteroid. It is a big asteroid discovered late, with too little time to respond. If a very large asteroid actually struck Earth, the consequences would depend on its size, speed, composition, and impact location, but at sufficient size, an impact would release an extraordinary amount of energy into the Earth's environment. The effects could extend far beyond the impact site, affecting atmosphere, climate, ecosystems, and human civilization. That is why planetary defense is not science fiction. It is risk management on a planetary scale. So, can humans stop a planet-killing asteroid? The honest answer is, potentially. We now have real evidence that a spacecraft can change an asteroid's motion. But there is no single guaranteed solution for every asteroid. Size, composition, orbit, and warning time can completely change the equation. And that's the key. We don't need to destroy the asteroid. We don't need to make it disappear. We simply need to make it miss. For most of human history, the sky was something we could only watch. Asteroids came. Asteroids went. And Earth simply wait. But something has changed. We have built machines that can leave our planet and travel across the solar system. We have reached asteroids. We have photographed them from close range. And in 2022, we deliberately changed the motion of one. It was a tiny experiment on a tiny asteroid. But it demonstrated something enormous. For the first time, humanity had demonstrated that Earth might not be completely helpless against the objects moving through space. The dinosaurs never had a planetary defense program. We do. The next dangerous asteroid may already be out there. The question isn't whether space contains dangerous rocks. We already know it does. The real question is whether we find it in time.